All right. In the previous video, we saw how we can describe the positions, velocities, and acceleration of a particle in different reference frames. And depending on the structure of the problem, one or the other could be suitable for that. And it is important to note that in those scenarios, we were just looking at frames that were rotating. Now we are dealing with a slightly different problem. To describe this, let me show you an example. This was the cart and pendulum system. I had this cart, a pendulum going around. So the motion of the tip of the pendulum is in general quite complex depending on the velocities and accelerations of the cart and angular velocities and acceleration of the pendulum. The pendulum could move in any weird direction. But it is important to remember that from a perspective of somebody sitting on the cart, the only thing they see is a pure rotational motion. So this relative motion is very easy to describe, and that's what we are trying to do, trying to use an intermediate frame to make calculation of complex movement easier. In dynamics, we usually want movements in inertia frame. Inertia frame because that's how, or the condition, necessary condition for the equations of motion, Newton's equation of motion, to be valid. But as this example shows, it is sometimes easier to measure movement in a local frame. So that's what we are trying to do, going from a local frame or a relative motion to inertia frame. In this diagram, I have the capital XYZ represent the parent frame, or the inertia frame in this case. And the orange little XYZ is a local frame that moves. So my local frame XYZ moves or translates and rotates, a very general case. And the inertia frame is this XYZ. So my goal here is to find positions, velocities, and acceleration in the inertia frame. So R, V, and A in inertia frame using relative measurements. That's measurement. So if an observer is sitting on the orange frame, that observer measures something about the movement of the particle, and using that knowledge and the knowledge of the movement of the observer itself, we want to infer the motion in the inertia frame. All right. So let's begin simple. Let me delete this. From just looking at the vectors, I can know that R, which is the position in the inertia frame, is position of the frame itself plus the relative position in that frame, rho. So this is good. Now, next one is velocity. Velocity is derivative of R, which is R dot plus rho dot. So R dot is the velocity of the frame itself in the inertial frame, and rho dot is a vector that is changing in a rotating frame. So we had this an equation for this before. It is r dot plus this rho dot is rho relative plus omega cross rho. And this omega is the angular velocity of the frame. Rho r is what the observer, this needs a dot, is what the observer sitting in the little xyz plane sees. And maybe it is important to note that this is the change inertia observer sees. This one is the change local observer where sees. And is there anything else I need to add? No, that's it. So that is the velocity. If I know how my frame is rotating and the information, the local measurement, I can infer the velocity in the inertial frame. And the last one is acceleration. Acceleration is v dot. I take derivative of this, so I have r double dot plus, because I cannot write dot easily on top of that, I write d over dt of this, whatever it is, rho dot of r, plus omega dot, or let me write it this way too, plus d over dt of this omega cross rho. So this rho dot relative, which is some rho dot 1, what do I write? I. Rho dot 1 I, it's rho dot relative is rho dot I plus rho dot 2 j plus, well, let me, I don't like the notation. Rho 1 dot I plus rho 2 dot j plus rho 3 dot k. So the components rho 1, rho 2, rho 3, time derivative of just those components. That's what it is. So it is a vector. It is like, I don't know, ai plus bj plus ck. It's a vector itself. So time derivative of that is, again, let's call it some a. This a dot is what is happening here. And again, I can write it as a relative dot plus omega cross a. And that's what I'm going to do. So this is going to be rho double dot relative, that is this one, plus omega cross rho dot relative And this one, I'm going to write it as omega dot cross rho plus omega cross rho dot. Again, same story. I have rho dot. This can be written as rho dot relative plus omega cross rho, and omega dot is the acceleration of the frame. So gathering everything, I will have r double dot plus omega dot cross rho plus what do I have? So I have this omega cross rho, omega cross rho plus what else? I have rho double dot relative plus 2 omega cross rho. This is extremely useful and very informative. Maybe let's take a moment to see what's happening. This one is acceleration of the frame or acceleration of the observer. This is the angular acceleration component, angular acceleration effect. This one, omega cross rho, is some kind of centripetal acceleration that the local observer sees. If you work it out, it is in the opposite direction of rho. The local or relative acceleration that the local observer sees, and this one is called Coriolis. Coriolis acceleration, which is a combined effect of this is rho dot, right? It must be rho dot. And it must be rho dot relative. Like this, yes, that's better. That makes more sense. So if I'm moving, I'm rotating, that is this omega, the observer rotates and also sees the particle moving in that frame. Even if the observer doesn't see an acceleration, just as a combination effect of rotation and this velocity, there is some acceleration observed in the inertia frame. Inertia frame. Okay, I think that's all I have here. So this is very useful. And one other thing I can add is usually we can have multiple intermediate frames and keep using these two equations for the velocity and acceleration in a cascading manner to go from a very remote local frame to the inertia frame. So that's it for now, and I see you in the next video.